Hi guys, so this video is looking at chapter 5.7, factorization of polynomials with complex numbers. I'm going to show you a couple of methods. I'm going to show you the completing the square method because that's my favorite. And I'm going to show you using the quadratic formula. This is just for simple polynomials. The other thing that I want to show you is I want to show you using the factor remainder theorem. Excuse me, to determine factors of more complex polynomials. So what we can do, let's just start off with a simple one. Solve 4z squared plus 4z plus 82 equals 0 over c using the completing the square method. So that's just a really fancy way of saying to complete the square. All right, so just as a reminder, when we complete the square, the coefficient of the leading digit we want to be 1. So I'm going to divide this whole thing through by 4. To give me, I need a different way to write these z's, I think. They look too much like my 2 sometimes. Z squared plus z, 82 divided by 4, 4 goes into 8 twice with no remainders, 4 goes into 2, 0 times, and then we would be left with 2, so that would be 2 over 4, so a half. Okay. So now what we're going to do, using the completing the square method, we're going to half this coefficient out the front here. So this is going to give us z plus 0.5. Then I'm going to square it. Now, to complete this square, I would have had to add 0.5 squared. So 0.5 squared is 0.25. So I would have had to add 0.25 to complete the square. So in order to keep that balanced, I'm going to subtract 0.25 outside the brackets as well. Okay, so then I should end up with z plus 0.5 squared plus 20.25 is equal to 0. All right, so let's move up over here. So then we would do z plus 0.5 squared is equal to negative 20.25. Then I'm going to take the square roots of both sides. So z plus 0.5 will be equal to the square root of negative 20.25. I'm just going to pop this in my calculator real quick. Now, when you do this on your calculator has 3 modes. So it's got the real mode and complex mode. So I'll just jump over to the calculator app and I'll show you how to change that. By the way, if you're ever curious about the model of calculator that I'm using, just look at the top here. This is the FXCG plus FXCG50AU. I think that most of you would have the CG50. Some people have the CG20. It's actually the exact same software and doesn't make a difference. Most Casios are pretty similar. All right, so let's pop this into complex mode. So we're just going to go into our normal run matrix mode. This was from the other day, so let's just clear all of that. Yes, I want to clear all. Now for this one here, you're looking up in this top screen. On my calculator that I'm looking in front of me in real life, I can see that it's got real mode. On this calculator here, I can see it's got A plus BI mode. And then the other mode would be the polar form, so the R cis theta mode. So to change that, we're going to go Shift, Setup, and then we're going to scroll down until we see complex mode. And we want to change that to A plus BI because we don't want it in polar form for this one. So now what we're going to do is we're going to do the square root of negative 0.25, and then this should give me a solution in complex mode. So 9 halves I. All right, so let's just jump back into our thing now and let's just write that. So z plus 0.5 was going to be equal to 9 halves, so that's the same as saying 4.5 I. The next thing I'm going to do is I'm going to subtract this from both sides. So I get z is equal to negative 0.5 plus 4.5 I. So this would be the complex solution for the first question using the completing the square method. Let's go ahead and let's have a look at this second one. So let's clear the screen and come back. I just say as an aside, I always forget the quadratic formula and I'm a maths teacher and I know that's terrible, but I always use other methods. I prefer factorization methods. I prefer completing the square because it's a process, and I remember the process. I can never remember the formulas. I always have to go look this up. Maybe I should get this tattooed on myself as well. Jesus. Okay, so here we go. So for this one, first thing I'm going to do is I'm going to have to expand those brackets so I can get it in the form ax squared plus bx plus c equals 0. So, or in this case, I should say az squared plus bz plus c equals 0. So this will be z squared plus 4z plus 29 is equal to 0. So that means a is equal to 1, b is equal to 4, and c is equal to 29. So if I substitute that into my quadratic formula, I'm going to get negative 4 plus or minus the square root of 16 minus 4 times a times c. So I'm going to do this one on my calculator. 4 times 1 times 29, and that's going to be minus 116. Divided by 2a, so a was equal to 1, so that's just divided by 2. All right, so next step, we're going to do negative 4 plus or minus square root of negative 100. Good, nice square number, I like that. Okay, so we can do this as negative 4 plus or minus 10i over 2. So I'm going to have two solutions for this one. I'm either going to have negative 4 over 2 plus 10i over 2, which is the same as saying negative 2 plus 5i. So that's my first solution, or my first root. The other solution could be negative 2 minus 5i, because we could have plus or minus there. So that would be how we solve that using the quadratic formula. I think I just realized that I've forgotten to find the positive or negative version of that here, but you guys get the point. One of these is going to be plus 4.5i, and one of them will be minus 4.5i for the two roots. Okay, so now let's have a go at a slightly more complex question. So we're going to use some factorization of polynomials stuff using that factor remainder theorem, using that long division that we've just looked at in the last two videos. This is an example of a complex, familiar type of question, and this is question 16 on page 304 for exercise 5.7. So this is using polynomial long division to calculate the roots for the polynomial, as well as using the factor remainder theorem. And in the question, they actually give us this nice little piece of information. So they've kind of already done the factor remainder theorem part for us. So just as a refresh for the factor remainder theorem, you look for factors of the constant. And then if I have, say for 306, obviously 3 is going to be a factor, and then 102 would be the other factor of that. So if I wanted to test if a function is divisible by a linear factor, then if it is divisible by a linear factor, it will have a remainder of 0. And to find that out, I'm going to substitute in f of a. And if f of a is equal to 0, then that means it has a remainder of 0, and therefore it's a factor. So what they have done is they've said that P3, when I substitute in 3, I get a remainder of 0. So therefore x, excuse me, x minus 3 must be a factor of this polynomial. Then it wants us to go ahead and find the other factors. Okay, so let's do this, and keep this in mind. Oh, sorry, this is not going to be x minus 3. This is going to be z minus 3. Keep in mind this is a complex number that we're dealing with now. Okay, so let's pop this out the front then. So we've got z minus 3 is our factor, and we need to use long division to solve. So I'm just going to type this all up. Then we'll just use that same process as before. So we do the division, then we multiply, then we subtract, and if we need to, we might add, but we'll probably just leave that last one off. Okay, so first things first, divide. So z fits into this, z to the power of 3 times. So that's the division. Then we're going to multiply. Z times by z to the power of 3 is z to the power of 4 minus 3z. So now we're going to subtract those two. And so z to the power of 4 divided, can't talk. Z to the power of 4 minus z to the power of 4 is 0. 10, I'm just going to say 10 plus 3 is going to be 13z cubed. Okay, so we've done those first 3 steps. Now let's go back, repeat the cycle, going from here. Z fits into 13z cubed, 13z squared times. Then we're going to multiply. So 13z squared times by the linear factor is going to give me 13z cubed minus 39z squared. and then we're going to subtract. So 13z cubed minus 13z cubed is 0. Well, that's rude. 25z squared minus negative 39 is the same as 25 plus 39, which is going to give me 64z squared. Okay, back to the beginning. So z fits into 64z squared, 64z times. 64z times by my linear factor is going to be 64z squared minus, oh, okay, I can't do this one that quick. So, where is it? There it is, negative 3 times by, what was my answer? 64 is going to be negative 192. Okay, this is getting a little crazy. Oh, and there's z there on the end. All right, I will have to grab the calculator out for these last couple, I think. Okay, so now we've done our division, we've done our multiply, now we're going to do our subtract. 64z squared takes 64z squared is 0. Negative 90z minus negative 192z is the same as negative 90 plus 192, so that's going to be 102z. Nearly there. Okay, back to the beginning. So we're going to do our division. So z fits into 102z 102 times. Our linear factor times by 102 is going to give me 102z minus, oh gosh, actually that's a nice easy one, 306. So we've done our multiplication. Last thing we're going to do is our subtraction. So negative 306 minus negative 306 is going to be 0. So that is the finished long division. So if I was to divide our polynomial from before by z minus 3, then the quotient or the solution is going to be z cubed plus 13z squared plus 64z plus 102. Okay, so I could rewrite this now, and I could rewrite this by popping this in brackets like this, but you can see that we haven't actually finished solving this because we need to go ahead and factorize the cubic function. Now, the cubic function is going to be a little bit trickier to factorize than a quadratic, so we're going to have to use the same process. We're going to have to use the factor remainder theorem to find factors of 102 that have a remainder of 0 when I substitute them into that new equation that we've just found, and then I'm going to have to use long division to determine the other linear and quadratic factors. So this is kind of a long one. So I'm going to clear the page. We'll come back from the beginning. All right, so just to clarify, this part is the part we are now trying to factorize. So I'm going to look at factors of the constant 102. So obviously I could have 1 or I could have 102. I could have 2 and I could have 51. Is this divisible by 3? Yes, it is. My little trick for finding out if things are divisible by 3, by the way, if you add up all the digits and the sum of the digits is something that's divisible by 3, then this is going to be divisible by 3 as well. So what do I mean by that? 1 plus 0 plus 2 is 3. 3 is divisible by 3, so 102 is divisible by 3 as well. Nice little trick for you. Unfortunately, I don't know what the other factor will be, 34, because I have my calculator here. Is it divisible by 4? 102 divided by 4? Nope. It's not divisible by 5. Is it divisible by 6? So 102 divided by 6 is going to be 17. So 6 and 17 are going to be other factors. I don't think it's going to be divisible by 7. Not many things are. No, it is not. I don't think it's going to be divisible by 8 either. No, it's not. It's not divisible by 9, not divisible by 10. I've checked most of the basic numerals. So let's go through and let's test some of these values. Okay, so if I'm dividing a function by a linear factor, I should get a remainder equal to 0. Oh my goodness. So what that means is if I substitute in f of a, I should get 0 as my answer. So let's try doing our polynomial divided by, let's just start off with a nice simple one and let's see if that's equal to 0. So what that means is we're going to find this particular value here and hopefully that will be equal to 0. So 1 cubed plus 13 13 times by 1 squared plus 64 lots of 1 plus 102. Okay, straight up, this is not going to be divisible. This is not going to be a factor because I'm keep adding numbers. It's not going to be anywhere close to 0. So I'm not even going to bother finishing that calculation. What I will test though is I will just change this. So if I divide this by a linear factor z plus 1, then I would substitute in -1. So now I'm just going to change all of these for a negative value, and this was at 64 times by 1, so this is going to be minus 64 now. So let's see if that's going to give us a remainder of 0. So -1 plus 13 minus 64 plus 102. Still don't think that's going to be balanced because that 102 is going to be a lot more than the minus 64. So those are not factors. So what did we try? We've tried we've tried z, because this is a complex number, plus 1. We've tried z minus 1, and neither of those two were factors. So now let's try dividing through by z minus 2. So this is a little bit of a long process, unfortunately, because we just kind of have to guess and check. I actually think the best way to do this might be using Excel, because I can do this really quickly. So let's just jump over to Excel. All right, so let's call this my value for z here. So I'm going to manipulate this in a second, and I'm going to write my function here. So this cell will be equal to the previous cell to the power of 3 plus 13 lots of the previous cell to the power of 2 plus 64 lots of the previous cell plus 102. And that's going to have some sort of error. Okay, let me just double check that I've done that right. Yep, they've put the times in there for me. That's what I've done wrong. Okay, so we had our different factors. So we had 1 and -1, which we tried. So if I pop those values in there, 1 was 180. So yep, there was no point checking that. -1 is 50. Okay, so that didn't work either, but we already knew that. So let's go back and pop some of our other values in. All right, so I've just used this formula in Excel, and I've just typed in a bunch of the factors, and we've worked out that -3 is going to be that solution. So if I jump back in here, I know that because I had f of x, or sorry, it's a polynomial of z, I should say, p of z, divided by z plus 3, I would have had to substitute p of -3 into my equation, and that is equal to 0. So therefore, z plus 3 is going to be the factor of this cubic function now. So now what we can do is we can go ahead and we can use that long division, and I might speed this process up just a little bit to save some time because this video is getting kind of long. Okay, so I've just gone ahead and I've finished off that long division. So we've got our quotient here. So remembering from that previous example, z minus 3 was our first factor, z plus 3 is our second factor, and we're left with a quadratic, z squared plus 10z plus 34. And now all we're going to have to do is factorize this quadratic. So do we have factors of 34 that are going to add to 10? Let me just think about this. 34, I could have 1 and 34. That's not going to add anywhere near to 10. I could have 2 and, 2 and a number is not going to add to 10. Why don't I just pop this into, I could do completing the square because I like that method. So z squared plus 5, that should be z plus 5 squared plus 34 will be equal to 0. Now I had to add 25 to finish completing the square, so I'm going to have to subtract 25 outside the square. So that's going to give me 9. So z plus 5 squared is going to be equal to -9 because I've moved that over to the other side. So z plus 5 will be equal to 3i. Oh no. Oh gosh, I'm going to have to pause the video here. I swear I am cursed. Yesterday, I just could not get anything to work, and I think today is just going to be another one of those days. I'll come back when this has sorted itself out. All right, apologies for that one. So it's back and working now. So I've just finished off that completing the square method. So I have z is equal to negative 5 plus 3i, so that's going to be one of my roots, and then the other root would be negative 5 minus 3i. So let's pop that back into our equation now. All right, so I just popped that, I've just popped that back into that factorized form now. So you can see here I've got z minus that root, z minus that root. So if I was to write the roots of all of that, so in other words, the solution to these numbers, I could have this root here. I'm actually cursed, I think, because they've just started doing some drilling as well. Oh my goodness gracious me. Okay, so that's my first root. That's a real number. Then I've got this next one. This is just using my null factor law, by the way. Equals negative 3, so second real root. And then we already knew the other two roots because we did that using completing the square. So negative 5 plus 3i. Oh my gosh. I'm going to have to finish this video up here, I think, guys, and I think I will do a complex unfamiliar example with you in the next video, so keep an eye out for that one. I'm going to have to move to a different building. Talk soon. See you later.